Good evening. My name is Brittany Fink, and today I will be discussing an energy analysis project on a polymer electrolyte membrane fuel cell for passenger vehicles. This project has been prepared for the UT Tyler Mechanical Engineering Department by also my partner Roberto Saenz and myself. The agenda for this presentation will be the introduction, followed by the motivation and key objectives, the background, benefits, drawbacks, analysis, references, and appendix. Firstly, what is a hydrogen cell? A hydrogen fuel cell is a power source that generates electricity through an electrochemical reaction by oxidizing hydrogen. In an ideal setting, the product of this reaction is water when the hydrogen bonds with the oxygen. Since water and heat are only the byproduct, fuel cells are to be very environmentally friendly compared to fossil fuels. The problem with fossil fuels is that when combusted for energy, harmful chemical byproducts are released into the environment. If more hydrogen fuel cells were used, we could reduce greenhouse gas production, which could in turn help reduce climate impact. Furthermore, fossil fuels also produce less energy per volume than a hydrogen fuel cell. The motivation to analyze the hydrogen fuel cell came from a variety of interests. Hydrogen fuel cells have a much higher energy-to-weight ratio than lithium-ion batteries. Implementing them into vehicles would reduce wear on both the road and the vehicle, and the reduced weight would make the vehicle easier to handle. Hydrogen fuel cells can also be refueled in a matter of minutes, versus a lithium-ion battery, which requires hours to recharge. A large factor for myself is that hydrogen can be found in the plethora of environments. Since this is the only element that exists as a single atom, it is easiest to form and bond across our universe. This opens up the possibilities of using hydrogen as a fuel source during space exploration. There are several key objectives that we hope to accomplish with this project. We will be conducting an analysis that shows how variances in fuel input, oxygen input, and temperatures affect the performance of the fuel cell. We will represent this fuel cell model by simulation using MATLAB. We will also assess the cost and maintenance between an FCV Toyota Camry and a Tesla lithium-powered vehicle, and address environmental impacts. As stated before, HFC creates electricity by an electrochemical reaction that oxidizes a hydrogen fuel source and only produces water and heat. If a hydrocarbon is used as a fuel source, the reaction will also produce carbon dioxide, along with water and heat. HFC has two plates, the anode and the cathode, separated by a proton and electrode membrane, or PEM. Hydrogen fuel is inputted at the anode side and oxidized at the cathode side with oxygen. As the hydrogen cations travel through the PEM, the electrons are removed from the cell through an external circuit. The hydrogen cations oxidize at the cathode to form water molecules. There are 5 types of fuel cells. We decided to pursue the PEMFC because it is the ideal for a passenger vehicle. It operates at a relatively low heat, and the PEM has durable electrolyte that isn't sensitive to carbon dioxide that may be present during operation. Some benefits are that it has no harmful emissions. Hydrogen fuel cells can be transported through our developed gasoline fuel infrastructure. Hydrogen fuel cells are very durable. Hydrogen is vastly abundant on our planet and solar system. Highly efficient, 40–60%, compared to combustion engine that's only 30–35%. It can be cogenerate system to produce electricity and heat. Overall, very environmentally friendly. But however, some drawbacks include newer technology, therefore it is currently very expensive. Few sources currently offering hydrogen fuel. Steam, methane, reforming to process hydrogen out of the methane results in a large amount of greenhouse gases, primarily carbon monoxide and carbon dioxide. Fossil fuels are used to produce hydrogen fuel. and hydrogen gas is highly flammable in the event of a catastrophic failure. Before we can begin the problem, we must set some assumptions. These include the ones listed here on the slide. Ideal gases, fluids are incompressible, fluids are inviscid, no external work, no friction or fouling in the system. System is a steady state operation and operating at STP. At the anode, the hydrogens feel protons and electrons are separated. The hydrogen cation travels through the proton electrolyte membrane, while the electrons are transferred through a wire as electricity to the peripheral or battery. At the cathode, the hydrogen cations react with the oxygen supply to produce liquid water as a byproduct, since we are operating under 100 degrees Celsius. Fuel cell efficiency can be calculated by multiplying three major efficiencies of a fuel cell system together. The three efficiencies pertain to the fuel cell's thermodynamics, voltage losses, and fuel utilization. These efficiencies will be described individually throughout the presentation. Fuel cells are very thermodynamically efficient, but as in every reaction, there is an energy loss by heat. The thermal efficiency of the fuel cell can be calculated easily by dividing the reaction's Gibbs free energy difference by the change in empathy of the reaction. Gibbs free energy difference was supplied in the textbook for liquid water, but the change in empathy needs to be calculated. The empathy of the reaction can be calculated using the following equation. The empathy values were gathered from the thermodynamic tables, and the numbers of the moles of each reaction and byproduct is determined from the chemical balance equation. The equation yielded us as an empathy reaction of 285.83 kilojoules per mole, and we converted that to negative 285,830 joules per mole. We plugged the value back into our thermal efficiency equations with the Gibbs free energy. This yielded us a thermal efficiency of 83%. The next efficiency we will be calculating is for voltage efficiency. The voltage efficiency of the fuel cell is dependent on the build requirements of the fuel cell itself. Electrolyte thickness and porosity index are a few factors that can affect the fuel cell's performance. Before we can begin analyzing the system, we have to define some variables regarding the system. These variables will be described as we go along, but the important ones to mention at the moment are a steady state as a standard temperature and pressure, STP. That is the atmospheric temperature and pressure, as well as a steady state current density of 10 milliamp per centimeter squared. We start by calculating the real voltage output of our PEMFC. The real voltage can be calculated by subtracting the voltage losses from theoretical thermal voltage output. These equations will be described on the following slides. The theoretical thermal voltage output can be calculated by dividing the negative of Gibbs free energy difference by the number of electrons multiplied by Faraday's constant. Gibbs free energy difference is the reference through the textbook and is temperature dependent. This equation yielded a value of 1.299 volts, but to get the actual voltage, we must start subtracting the system's voltage losses. The first of the voltage losses is the activation voltage loss, or activation over voltage. This is an energy used to prep the electrolyte for chemical reactions to occur. To solve for overvoltage, we'll be using the Butler-Volmer equation. This equation is a bit complex, but it will be simplified after considering the parameters of our theoretical fuel cell. The first parameter is to address our alpha. Since our alpha is equal to 0.5, the reaction is symmetrical. This means that the forward and reverse currents are identical, and only one side needs to be analyzed. The second condition is a steady state, meaning there is no change in the current density. JSS is equal to J. This implies to the equation below. This simplified Butler-Volmer equation can be solved relatively easily. As you can see, the activation over voltage is a temperature and current related. Higher operating temperatures and current densities will require a higher activation voltage loss. All variables are known or given, and the final value of 0.473 is calculated. The next voltage loss to calculate is the charge transportation losses across the electrolyte membrane. This equation introduces a new variable, the area-specific resistance, or ASR ohmic. This variable can be calculated by dividing the membrane thickness by the membrane conductivity. Both of these values are given in the system parameters. This produces an ASR of 0.1 ohms centimeter squared. With the variable known, we continue to the transportation voltage loss equation. This is solved by multiplying the current density and the ASR ohmic. This provides a loss of 1 MV. The last voltage loss to calculate is the voltage losses due to reactant depletion in the catalyst. This equation is shown below. As you can see, there is an unknown variable for limiting current density, JL, that we must calculate for. The limiting current density can be solved using the following equation, which introduces another unknown variable, DEF. DEF, or effective diffusivity, can be solved with the following equation, which presents us with another unknown, the nominal diffusivity at the catalyst, Dij. The nominal diffusivity, or binary diffusion coefficient, can be calculated using the following equation. It is a busy equation, but all variables are known or can be referenced through literature. As you can see, this equation is dependent on critical temperatures, pressures, and molecular weight. The parameters A and B are specific to the equation, which is based on the kinetic theory of gases at low pressures. After plugging in all the values, we get a binary diffusion coefficient of 0.810 centimeters squared per second. With our nominal diffusivity known, we can plug it back into the effective diffusivity equation that is based on our Brugman correction. In this equation, multiplying the nominal diffusivity by the porosity of the electrode raised to a power of 1.5, the porosity of the ratio between pores and total volume on the electrode. This equation yields us an effective diffusivity of 0.205 centimeters squared per second. With our effective diffusivity known, we calculate our limiting current density. The limiting current density, JL, is the condition that will occur when the reactant concentration in the catalyst drops to 0. This represents the highest current density to the fuel cell could physically reach. All factors have been used before except the bulk flow reactant concentration, CR, and electrode thickness. With these parameters plugged in, we yield a limiting current density of 5 amps per centimeter squared. Now that we know our limiting current density, we can now calculate the voltage losses due to the reactant depletion in the catalyst. In this equation, C is the geometric concentration loss coefficient. After plugging in the values, we obtain a loss of 0.2 MV. Now that we have all our voltage losses calculated, we can return to the original equation to obtain the actual voltage of the fuel cell. After plugging in the voltages into the equation, we get an actual voltage of 0.755 volts. Plugging this back into the voltage efficiency equation, V actual over E thermal, we obtain an electric efficiency of 61.4%. The fuel utilization can be solved with the following equation. In the numerator, we have a current divided by the number of electrons and Faraday's constant. In the denominator, we have a hydrogen fuel rate supply given in moles per second. Current can be found by multiplying the current density by the area of the electrode. For our theoretical fuel cell, we used a fuel utilization of 95%. Now that we know our various efficiencies, we can multiply them together to determine our fuel's total efficiency. By doing so, we get a total efficiency of 48.4%. The values we obtain from our theoretical fuel cell vary a bit from what a PEMFC should produce. A typical fuel cell usually produces an actual voltage with a range of 0.4 to 0.7 V. Ours produced 0.755 volts, which is slightly higher than the typical. The efficiency of our system is within the range of a typical PEMFC. I believe we can achieve better performance for our fuel cell if we operated at a slightly higher temperature. We have begun MATLAB simulation, but haven't made much progress to present that at the moment. Here we show our references. This displays our Gantt chart and our timeline. Our next final report submission for everything will be due December 7th. And Appendix B includes our equations, just formulated properly in the correct order so you can see them.